Okay, for this problem we have a weak acid, HF, and we are trying to solve for Ka, and we know the pH and the concentration. So we're essentially solving for the Ka of a weak acid based off of the pH and the concentration. So, in previous problems we have done the assumption first, but we can't do that here. The assumption was taking the molarity divided by Ka and checking to see if it's bigger than 100. We don't have that, but it turns out it's not a problem. So, the rest of the problem is actually set up pretty much the same. So, write out the balanced equation. It's still an ice method problem. This is a weak acid. You're going to put it in water, which is a liquid, which we will ignore. This is going to be our base in this situation. Okay. This will lose an H plus and become F minus, and this will become H3O plus, which makes perfect sense because it's an acid. We should be producing H3O plus, which is why we get a pH. Okay. Not that it matters for this problem, but this is the conjugate base. This is the conjugate acid. Okay. Ice method. The initial concentration is 0.750 molar. We don't care about that, and this is 0, and this is 0. This is going to decrease by some amount. This is going to increase by the same amount. Both of those are. And honestly, we don't know these numbers yet. So basically, this is 0.750 minus x. This is x, and this is x. So the Ka that we're solving for is products over reactants. X squared divided by 0.750 minus x. In previous problems we had at Ka and needed to solve for x. This time we need to figure out x so that we can solve for Ka. But the beauty is, because we know the pH and it is related to the concentration of H3O plus, we can directly solve for x. So pH is equal to the negative log concentration of H3O plus. We know pH, which is 1.65, is equal to negative log concentration of H3O plus. This is really similar to the previous problem of solving for molarity from pH, so a few videos ago. So first thing we're going to do is get rid of the negative sign by multiplying by -1 on both sides. This side becomes positive. Now we need to get rid of this logarithm by raising both sides to the 10. This will cancel out, and concentration of H3O plus, which is x, will be equal to 10 raised to the negative 1.65. So 10 raised to the negative 1.65. And our x value, or our concentration of H3O plus, is equal to 0.022387, whatever. More sig figs than we need, but that's okay. But the beauty is, this is equal to x, because that's how our problem was set up. H3O is equal to x. So we basically just plug this in for all these x's and solve for Ka. And that's the end of the problem. So Ka is equal to 0.022387 squared, because x is squared there, divided by 0.750 minus 0.022387. So the assumption was to get rid of this minus x at the bottom. It turns out it doesn't matter for this one because we're going to solve for x anyway, and it's just easy to subtract it off. So plugging all of this in, see what happens. So it's going to be that number squared divided by 0.750 minus 0.0223872114. We're going to plug it all in, which should be what we have over there, right? Hit enter. It comes out to 6.888 times 10 to the negative fourth. We basically get 3 sig figs, so 6.89 times 10 to the negative fourth. So, despite being a very different looking problem than the previous ones, it's actually probably easier because we know the pH, we can solve for x and just plug that in. We don't have to worry about the quadratic. We don't have to worry about whether the assumption thing works. This problem just works out pretty nicely. So basically we have a weak acid. Since we can solve for H3O plus, we can solve for x, plug it in, and we get Ka.